A photon has no mass. It has no internal parts. You cannot open one up and look inside. It carries no hidden fuel, no battery, no reservoir of stored substance. And yet, a single gamma-ray photon can carry tens of millions of times more energy than a photon of visible light. Enough energy to shatter atomic nuclei. Enough to be individually detected by instruments on Earth from sources billions of light years away. A photon from a radio tower carries so little energy that trillions of them together can barely warm a grain of dust. Both are photons. Both are fundamentally the same kind of thing. So where does that energy actually come from? Not what energy does, not how we measure it, but where does a photon get it in the first place? The answer turns out to be one of the most elegant ideas in all of physics, and it changes how you understand light, matter, and the very nature of energy itself. If you find this kind of deep exploration fascinating, a quick like or subscribe genuinely helps the channel grow. It's a small thing, but it makes a huge difference. Now, let's begin. Let's start with a deceptively simple question. What is a photon? You've probably heard the word before. You might have heard that light is made of photons, that photons travel at the speed of light, that photons have no mass. All of that is true, but none of that tells you what a photon actually is. None of it explains where the energy comes from, and that's the question that pulls on a thread running through some of the deepest ideas in modern physics. Most people picture a photon as a tiny glowing ball shooting through space, a little pellet of light, something you could, in principle, hold in your hand if your fingers were small enough. This image is intuitive, and it is completely wrong. A photon is not a tiny object. It's not a container carrying energy the way a box carries cargo. If you start with that picture in your head, you will never understand where photon energy comes from, because you'll be looking for a fuel tank inside something that doesn't have an inside. So let's set that image aside and build the correct picture from the ground up. To understand what a photon actually is, you first need to understand the thing it is made of. Not matter, not substance, something more fundamental: the electromagnetic field. The electromagnetic field is one of the most important concepts in all of physics. It's a real physical entity that fills the entire universe. It exists everywhere, at every point in space, at every moment in time. You cannot see it directly, you cannot touch it, but you interact with it constantly. Every time you see color, feel warmth from sunlight, use a phone, listen to a radio, charge a battery, or flip a light switch, you are interacting with the electromagnetic field. It is not an abstraction. It is not a mathematical convenience. It is as real as the chair you're sitting in, even though it's a very different kind of thing. The idea of fields in physics goes back to the 1800s. Before fields, scientists thought forces acted at a distance. If the sun pulls on Earth, somehow that pull reaches across 93 million miles of empty space instantly, with nothing in between carrying it. Isaac Newton himself was uncomfortable with this idea. He called it philosophically absurd. But he couldn't explain what was doing the pulling, so he left the question open. It was Michael Faraday, working in the early to mid-1800s, who changed everything. Faraday was a brilliant experimentalist who thought not in equations, but in pictures. He imagined invisible lines of force radiating outward from electric charges and magnets, filling the space around them. These weren't just visualization tools. Faraday believed they were real physical things. The space around a magnet wasn't empty, it was filled with a field that carried the magnetic influence from one place to another. Most physicists at the time dismissed the idea, but Faraday's intuition was deeper than he could express mathematically. It took another physicist to put his vision into precise language. James Clerk Maxwell, a Scottish physicist working in the 1860s, took Faraday's field lines and turned them into a set of equations. Maxwell's equations are among the most beautiful and powerful in all of physics. They describe how electric and magnetic fields are created, how they interact with each other, and how they change over time. Maxwell showed something extraordinary. Electric fields and magnetic fields are not separate things. They are two aspects of a single unified entity, the electromagnetic field. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. The two are woven together, each generating the other in an endless feedback loop. And then Maxwell made a prediction that stunned the scientific world. His equations showed that these interlocked electric and magnetic fields could propagate through space on their own, without any wires or charges to carry them. They could ripple outward like waves on a pond, traveling at a specific speed. Maxwell calculated that speed from the constants in his equations, and the number he got was approximately 300,000 kilometers per second. The speed of light. This was not a coincidence. Maxwell realized that light itself is an electromagnetic wave. The light you see with your eyes, the warmth you feel from a fire, the radio signals carrying music to your car, the X-rays at your dentist's office, the gamma rays from radioactive decay, all of these are the same fundamental thing. They are all ripples in the electromagnetic field, differing only in how fast they oscillate. The electromagnetic field isn't just relevant to understanding photons, it is the medium from which photons are made. A photon is a ripple in this field, not a ripple traveling through the field the way a wave travels through water. A photon is the ripple itself. The field is not a medium that photons move through. The field is what photons are excitations of. This is a subtle but critical distinction. When a wave travels across the surface of a lake, the water is the medium. The wave is a disturbance in the water. You can separate the concept of the wave from the concept of the water. The water exists whether or not there are waves. But a photon's relationship to the electromagnetic field is different and deeper. In quantum field theory, the most precise framework we have for describing nature at the fundamental level, particles are not objects sitting in fields. Particles are the fields, or more precisely, they are quantized excitations of the fields. An excitation is a specific, discrete packet of vibration in the field. The electromagnetic field can vibrate, and when it does, those vibrations come in specific, indivisible units. Each unit is a photon. Think about it this way. Imagine a perfectly calm lake. No wind, no disturbances. The surface is flat. This is like the electromagnetic field in its lowest energy state, its ground state. Now imagine you drop a stone into the lake. A ripple spreads outward. That ripple is a disturbance, an excitation of the water's surface. The ripple carries energy. The energy came from the stone, from the act of dropping it, from the process that created the disturbance. The ripple doesn't contain a little engine inside it. It doesn't have a fuel supply. The energy is in the shape of the disturbance itself, in the fact that the surface is no longer flat, in the motion and displacement of the water. A photon is something like that ripple, but with a crucial quantum twist. The electromagnetic field doesn't allow arbitrary disturbances. You can't have half a ripple or a third of a ripple. The field's excitations come in discrete, indivisible packets. You can have 1 photon, or 2 photons, or 1 billion photons, but you cannot have 1.5 photons. This discreteness, this quantization, is one of the defining features of quantum physics. And it's why we talk about photons as individual things at all, rather than just talking about electromagnetic waves. But here is where people get confused. Because we call a photon a particle, because we give it a name and count it as a thing, our brains naturally want to treat it as an object. A tiny thing with an inside and an outside, a little container. And once you start thinking of it as a container, The question of where its energy comes from seems to demand a physical answer. There must be something inside the photon that provides the energy. Some internal mechanism, some fuel, some substance. But there isn't. A photon has no internal structure. It has no parts. There is nothing inside it. The energy of a photon is not stored inside the photon, the way gasoline is stored inside a fuel tank. The energy is the excitation itself. It is the fact that the electromagnetic field is vibrating at a particular frequency. The energy is a property of the disturbance, not a substance contained within it. This is genuinely difficult to wrap your mind around. We are physical creatures who evolved in a world of objects. We understand energy in terms of things. A battery has energy stored in chemical bonds. A compressed spring has energy in its deformation. Food has energy in molecular structures. In every case, energy is something contained in something else. A photon breaks this pattern completely. There is no container. There is only the vibration. The energy is what makes the photon exist. Without the energy, there is no excitation. Without the excitation, there is no photon. In a very real sense, the photon is energy, a quantum of energy in the electromagnetic field. Let's make sure this is concrete. The electromagnetic field is everywhere. Right now, in the room where you are, the electromagnetic field exists at every point. It's in the air, in the walls, inside your body, in the space between atoms. Most of the time, at most points, it's in its ground state, its lowest energy configuration. But when something disturbs it, when a charged particle accelerates, when an electron drops to a lower energy level in an atom, when a nuclear reaction releases energy, the field gets excited. A ripple forms. That ripple is a photon. The photon then travels through space at the speed of light. Not faster, not slower. Exactly at the speed of light. Always. It doesn't accelerate from rest to light speed. It doesn't slow down and then speed up. From the instant it comes into existence, it moves at 300,000 kilometers per second. This isn't a choice the photon makes. It's a consequence of having no rest mass. Massless excitations of fields must travel at the speed of light. It's built into the structure of space-time itself. As the photon travels, it carries the energy of its excitation with it. When the photon is absorbed, when it hits an atom or a molecule or your retina, that energy is transferred to whatever absorbed it. The photon ceases to exist, but the energy doesn't vanish. It goes into the absorbing system. It might raise an electron to a higher energy level. It might heat a surface. It might trigger a chemical reaction in your eye that allows you to see. Energy is conserved. It moves from the field to the matter, carried by the photon. This picture, a photon as a quantized excitation of the electromagnetic field, is not a metaphor. It is not an approximation. It is the description that emerges from quantum electrodynamics, often called QED, which is the quantum field theory of the electromagnetic interaction. QED is one of the most precisely tested theories in the history of science. Its predictions have been verified to better than 10 parts in a billion. When QED tells us that a photon is an excitation of the electromagnetic field, that statement has been tested and confirmed with extraordinary precision. Now, you might wonder how scientists arrived at this understanding. The story stretches back more than a century and involves some of the most dramatic intellectual revolutions in scientific history. By the late 1800s, Maxwell's theory of electromagnetism was solidly established. Light was understood as an electromagnetic wave. Experiments by Heinrich Hertz in 1887 confirmed that electromagnetic waves could be generated, transmitted, and detected, exactly as Maxwell's equations predicted. The wave picture of light seemed complete. Light was a wave. Waves have frequencies and wavelengths and amplitudes. Everything made sense. But then, right at the turn of the 20th century, cracks appeared. Certain experiments produced results that the wave theory of light simply could not explain. These weren't small discrepancies. They were fundamental failures of the theory to account for observed reality. One of the most important was the black body radiation problem. Every object that has a temperature emits electromagnetic radiation. You emit infrared radiation right now. A hot piece of metal glows red, then orange, then white as it gets hotter. The sun emits radiation across a broad spectrum. Physicists in the late 1800s tried to calculate how much radiation an ideal emitter, a so-called black body, should produce at each frequency. Classical physics, using Maxwell's electromagnetic theory and the laws of thermodynamics, made a clear prediction. And the prediction was catastrophically wrong. Classical theory said that as you go to higher and higher frequencies, the amount of radiation should increase without limit. At ultraviolet frequencies and beyond, an ideal emitter should radiate infinite energy. This was called the ultraviolet catastrophe. Obviously, real objects don't emit infinite energy. The prediction was absurd. Something was deeply wrong with the classical picture. In 1900, the German physicist Max Planck found a way to fix the calculation. But his fix was strange. Planck assumed that the electromagnetic field could only emit and absorb energy in discrete chunks, not continuously. Each chunk had an energy proportional to the frequency of the radiation. The proportionality constant was a new fundamental number, which Planck called h. Today, we call it Planck's constant. With this assumption, Planck's formula matched the experimental data perfectly. The ultraviolet catastrophe was resolved. But Planck himself wasn't sure what his assumption meant physically. He treated it almost as a mathematical trick, a convenient device to make the equations work. He didn't claim that light itself came in discrete packets. That step was taken 5 years later by someone else. In 1905, Albert Einstein published a paper on what is called the photoelectric effect. When you shine light on certain metals, electrons are ejected from the surface. This was known experimentally, but the details didn't match the wave theory of light. According to wave theory, brighter light should give each electron more energy. But experiments showed that brightness didn't affect the energy of individual electrons at all. Instead, it was the frequency of the light that mattered. Below a certain frequency, no electrons were ejected regardless of how bright the light was. Above that frequency, electrons were ejected immediately, even with very dim light. Einstein explained this by proposing that light itself comes in discrete packets. Each packet, which we now call a photon, carries a specific amount of energy determined by its frequency. When a photon hits an electron in the metal, it transfers all of its energy to that electron. If that energy is enough to overcome the forces binding the electron to the metal, the electron escapes. If not, the electron stays put. This explained everything. Higher frequency means more energy per photon, which means electrons are ejected with more kinetic energy. Higher brightness means more photons, not more energy per photon. So more electrons are ejected, but each one has the same energy. This was one of the foundational moments of quantum physics. Einstein was essentially saying that the electromagnetic field is quantized. Its energy comes in indivisible units. Each unit is what we now call a photon. For this work, not for relativity, Einstein received the Nobel Prize in Physics in 1921. But notice something important about what Einstein showed. The photon's energy is set by its frequency, not by how bright the source is, not by how far the light has traveled, not by anything hidden inside the photon. The energy is determined by a single property: how rapidly the electromagnetic field is oscillating in that particular excitation. A high-frequency photon is a rapidly oscillating excitation and carries a lot of energy. A low-frequency photon is a slowly oscillating excitation and carries very little energy. The frequency is not a label attached to the photon. The frequency is the photon. It defines the excitation completely. This is a profound point that gets lost in simplified explanations. When someone says a photon carries energy, it's natural to imagine the photon as a vehicle and the energy as cargo. But that's not what's happening. The energy isn't riding along inside the photon. The energy is the oscillation. The photon is the oscillation. They are the same thing, described from different angles. Think again about that ripple on a lake. The ripple has energy. You can measure the energy by seeing how high the water rises, how fast it moves. But you can't separate the energy from the ripple. You can't pour the energy out of the ripple and keep the ripple going without it. The energy is in the motion and displacement of the water. The ripple is the motion and displacement of the water. Remove the energy and the ripple ceases to exist. The water goes flat again. A photon works the same way. The energy is in the oscillation of the electromagnetic field. The photon is the oscillation of the electromagnetic field. Remove the energy and there is no photon. The field returns to its ground state. This is why asking where the energy is stored inside a photon is like asking where the wetness is stored inside a single water molecule. The question assumes a structure that isn't there. A water molecule isn't wet. Wetness is an emergent property of many water molecules interacting with a surface. Similarly, a photon doesn't contain energy as a hidden internal substance. Energy is an intrinsic property of the excitation itself. Now, there's another important feature of photons that makes them different from the everyday objects we're used to. A photon has no rest mass. 0. This is not an approximation. It is exact. The rest mass of a photon is precisely 0. This seems like it should be a problem. In everyday life, we associate energy with massive things. A truck has kinetic energy because it's heavy and moving. A ball sitting on a shelf has gravitational potential energy because it has mass and is elevated above the ground. Food has chemical energy stored in molecular bonds between atoms with mass. Mass and energy seem inextricably linked, but they are not. Or more precisely, mass is one way to have energy, but it's not the only way. A photon demonstrates this beautifully. It has 0 rest mass, yet it carries energy. How? Because its energy comes from its frequency, from the oscillation of the electromagnetic field, not from any mass. A photon's energy is entirely kinetic in a certain sense. It is the energy of the field vibrating at a particular rate. No mass is required for this. The field vibrates, the vibration propagates, energy moves from one place to another. The machinery of the universe doesn't require mass for energy to exist. This is something that confused physicists for a long time, and it still confuses many people today. We grow up learning that energy equals 1/2 mass times velocity squared, the formula for kinetic energy in classical mechanics. That formula has mass in it. If mass is 0, the energy should be 0. But that formula is an approximation. It works beautifully for everyday objects, for baseballs and cars and planets. It fails for photons. For massless particles traveling at the speed of light, the rules are different, and the relevant equations come from Einstein's special relativity. We'll explore those equations shortly. For now, the key point is that mass is not required for energy. A photon proves this every time it warms your skin or triggers a receptor in your eye. So let's take stock of where we are. A photon is a quantized excitation of the electromagnetic field. The electromagnetic field is a real physical entity that fills all of space. When something disturbs the field, when a charged particle accelerates, or an electron changes energy levels in an atom, the field vibrates. Those vibrations come in discrete, indivisible packets. Each packet is a photon. The photon has no rest mass, no internal structure, no hidden compartments. Its energy is not a substance stored inside it. Its energy is a property of the vibration itself, determined by how rapidly the field oscillates. This is what a photon is in physically meaningful terms. Not a tiny glowing ball, not a container of energy, a quantum of vibration in a field that fills the universe. And already, embedded in this picture, is a hint about where the photon's energy comes from. The energy comes from whatever disturbed the field, whatever caused the excitation, whatever made the ripple. A photon doesn't generate its own energy. It doesn't pull energy from nowhere. It gets its energy from the physical process that creates it. An electron dropping between energy levels in an atom, a particle accelerating in a magnetic field, a nuclear reaction releasing binding energy. Each of these is a process that excites the electromagnetic field, and the energy that goes into the excitation becomes the energy of the photon. But to understand this fully, we need to understand the one property that completely determines how much energy a photon carries. The property that Einstein identified and that Planck first hinted at. The property that connects the quantum world to the wave world. Frequency. And frequency turns out to be far more interesting than most people realize. If a photon's energy is not a substance hidden inside it, if it's not fuel or cargo or some tiny battery, then what determines how much energy a photon carries? The answer is a single property: frequency. And this one word, frequency, contains within it the entire explanation for why a gamma-ray photon can shatter a molecule, while a radio wave photon can pass through your body without you ever noticing. They are both photons. They are both excitations of the exact same electromagnetic field. The only difference between them is how fast the field is oscillating. That rate of oscillation is frequency, and it determines everything. Let's start with what frequency actually means. Not as a formula, not as a number you plug into an equation, but as a physical thing happening in the real world. Imagine you're holding a rope tied to a wall. You flick your wrist up and down, and a wave travels along the rope toward the wall. Now flick your wrist slowly, once per second. A lazy, slow wave moves along the rope. The peaks are far apart. The motion is gentle. Now flick your wrist fast, 10 times per second. The waves are bunched together. The peaks are close. Your hand is doing more work. You're pumping more energy into the rope with each passing second. That rate, how many complete oscillations happen per second, is the frequency. One oscillation per second is 1 Hertz, named after Heinrich Hertz, who first generated and detected electromagnetic waves in 1887. A million oscillations per second is 1 megahertz. A billion is 1 gigahertz. The higher the frequency, the more rapidly something is oscillating. For a wave on a rope, this is fairly intuitive. You can see the difference between a slow wave and a fast wave. You can feel the difference in effort required to produce them. Fast waves take more energy. You have to move your hand faster and harder. This isn't some mysterious quantum effect. It's basic mechanics. A faster oscillation requires more energy input. That's true for ropes. It's true for sound waves. It's true for water waves. And it's true for the electromagnetic field. When the electromagnetic field oscillates, it produces an electromagnetic wave. The frequency of that wave is how many times the electric and magnetic fields complete a full cycle of oscillation per second. A radio wave might oscillate at a frequency of 100 million Hertz. That's 100 million complete cycles per second. Visible red light oscillates at about 430 trillion Hertz. Violet light is around 750 trillion Hertz. An X-ray might oscillate at frequencies in the range of 100 quadrillion to 10 quintillion Hertz. A gamma ray goes even higher. These numbers are almost impossible to grasp intuitively. 430 trillion oscillations per second. Nothing you can touch or build vibrates that fast. And yet, that is what red light is. The electromagnetic field vibrating 430 trillion times every second. Each complete vibration is a cycle. The distance the wave travels during one cycle is the wavelength. For red light, about 700 nanometers, roughly 1/100th the width of a human hair. Now here is the key insight. The relationship between a photon's frequency and its energy is not complicated. It is one of the simplest and most important equations in all of physics. The energy of a photon equals Planck's constant multiplied by the photon's frequency. That's it. E equals h times f. Nothing else enters the equation. The energy depends on one thing and one thing only: frequency. Planck's constant is a fixed number. It never changes. It's the same everywhere in the universe, at all times, under all conditions. It's one of the fundamental constants of nature, like the speed of light or the gravitational constant. Its value is approximately 6.626 times 10 to the negative 34 joule seconds. That is an extraordinarily small number. Written out in full, you would need a decimal point followed by 33 zeros before you reached the significant digits. This tiny number is why quantum effects are invisible in everyday life. The energy packets are incredibly small at the frequencies we encounter, but the number is not zero, and that matters enormously. Because Planck's constant is not zero, the energy of an electromagnetic excitation cannot be arbitrary. It comes in discrete chunks. You cannot have a photon with any energy you like at a given frequency. At a particular frequency, every photon has exactly the same energy. No more, no less. You can have more photons, which increases the total energy, but each individual photon at that frequency carries precisely the energy given by Planck's constant times the frequency. This is quantization. This is why we call them quanta. Let's put some real numbers to this to see what it means in practice. Consider a photon of red light with a frequency of about 430 trillion hertz. Multiply that by Planck's constant, and you get an energy of roughly 2.8 times 10 to the negative 19 joules. That is an absurdly small amount of energy by everyday standards. A joule is roughly the energy it takes to lift an apple 1 meter. A single photon of red light carries less than a billionth of a joule. It's almost nothing. But now consider a gamma-ray photon with a frequency of, say, 3 times 10 to the 20 hertz. That's 300 quintillion oscillations per second. Multiply by Planck's constant, and you get an energy of about 2 times 10 to the negative 13 joules. Still tiny in absolute terms, but nearly 1,000,000 times more energy than the red light photon. And at the very highest energies observed in nature, gamma-ray photons from cosmic sources carry energies trillions of times higher than visible light photons. What changed? Not the nature of the photon, not its structure, not some internal mechanism. The only thing that changed is the frequency. A gamma-ray photon is the electromagnetic field oscillating incredibly fast. A radio wave photon is the electromagnetic field oscillating incredibly slowly. The faster the oscillation, the more energy the excitation carries. The relationship is perfectly linear. Double the frequency, double the energy. Triple the frequency, triple the energy. 10 times the frequency, 10 times the energy. It's that simple and that absolute. Now, this raises a question that's worth thinking about carefully. Why should higher frequency mean more energy? What is it about faster oscillation that carries more energy? Is there a deeper explanation? Or is this just a brute fact about the universe? There's a way to develop intuition here, even though the full answer involves the mathematical structure of quantum field theory. Think back to the rope analogy. When you oscillate a rope slowly, the wave is gentle. The rope moves up and down a small amount per unit time. The rate at which energy flows along the rope is low. When you oscillate the rope quickly, everything moves faster. The rope is yanked up and pulled down more rapidly. The tensions are higher. The rate of energy transfer is higher. You're doing more work per second to maintain the oscillation. For the electromagnetic field, something analogous happens. A higher frequency oscillation means the electric and magnetic fields are changing more rapidly at every point the wave passes through. The rate at which the field configuration shifts is greater. In classical electromagnetic theory, the energy carried by a wave depends on the amplitude, how large the oscillation is, not on the frequency. But in quantum theory, something new enters. The field is quantized. Energy can only come in packets, and the size of each packet is proportional to frequency. This means the minimum possible energy at a given frequency, the energy of a single photon, is set by the frequency. You cannot have less than one quantum, and each quantum's energy is h times f. At higher frequencies, the minimum energy is higher. The quantum steps are bigger. Each individual excitation carries more energy. This connection between frequency and energy was not obvious to anyone before Planck. Classical physics treated energy as continuous. You could have any amount of electromagnetic energy at any frequency. There was no minimum, no quantum, no packet. The idea that energy comes in discrete lumps was revolutionary when Planck introduced it in 1900, and it remained controversial for years. Even Planck himself was reluctant to accept the full implications. He treated his quantization assumption as a mathematical device, not a physical reality. It was Einstein who, 5 years later, took the idea seriously as a description of how the electromagnetic field actually behaves. The field doesn't just interact in quanta, it is quantized. The excitations are discrete. Each one has an energy determined by frequency. This is not a feature of the measuring process, it is a feature of reality. But why does the electromagnetic field only vibrate in whole quanta? Why can't you have 1.5 photons, or 2/3 of a photon? This is one of the most natural questions anyone can ask, and the answer goes deeper than most explanations offer. The key lies in the mathematical structure of the field itself. The electromagnetic field at any point in space behaves mathematically like a harmonic oscillator. A harmonic oscillator is anything that vibrates back and forth around an equilibrium position with a restoring force proportional to how far it's displaced. A pendulum is a harmonic oscillator. A weight bouncing on a spring is a harmonic oscillator. A guitar string vibrating is a harmonic oscillator. These systems are everywhere in physics, and they all share the same underlying mathematics. In classical physics, a harmonic oscillator can have any energy. You can push a pendulum gently and give it a little energy, or push it hard and give it a lot. The energy varies continuously. There are no gaps, no jumps, no forbidden values. But in quantum mechanics, something changes. When you apply the rules of quantum mechanics to a harmonic oscillator, you discover that its energy can only take specific discrete values. The oscillator can have 1 quantum of energy, or 2 quanta, or 3, but never 1.5 or 2.7. The energy comes in steps, evenly spaced, each step separated by an amount equal to Planck's constant times the oscillator's natural frequency. This isn't an assumption imposed on the mathematics. It falls out of the equations automatically when you solve the quantum version of the harmonic oscillator problem. The discreteness is a consequence of the wave-like nature of quantum systems, and the requirement that the wave function remain well-behaved and normalizable. It's as inevitable as the fact that a guitar string can only vibrate at certain harmonics. A string fixed at both ends can vibrate at its fundamental frequency, or at twice that frequency, or 3 times, but not at 1.5 times. The boundary conditions force the vibration into discrete modes. Quantum mechanics does something analogous to the electromagnetic field. The boundary conditions of quantum theory force the field's energy into discrete levels. Each level corresponds to a specific number of photons. 1 quantum of energy is 1 photon. 2 quanta is 2 photons. 0 quanta is the vacuum, the field in its ground state with no photons at all. The quantization of the electromagnetic field is not a postulate. It is a mathematical consequence of applying quantum mechanics to a system that oscillates. Now let's explore the electromagnetic spectrum, because seeing how a single phenomenon spans such an enormous range of frequencies and energies makes the role of frequency vivid and concrete.
At the very lowest frequencies, we have radio waves. These are electromagnetic field oscillations with frequencies from about 10,000 Hz up to around 300 billion Hz. Radio waves are used for broadcasting, communication, and radar. Their photons carry extremely little energy. A single radio wave photon at the frequency of a typical FM radio station, about 100 million Hz, has an energy of roughly 6.6 times 10 to the negative 26 joules. That is so little energy that individual radio photons are essentially undetectable one at a time. Radio communication works because trillions upon trillions of photons are produced simultaneously by the transmitter. The collective effect is what your radio receives. Moving up in frequency, we reach microwaves. These have frequencies from about 300 million to 300 billion Hz. Your microwave oven operates at about 2.45 GHz, roughly 2,450,000,000 Hz. Each microwave photon carries slightly more energy than a radio photon, but still an incredibly tiny amount. The reason a microwave oven can heat food isn't that individual photons are powerful. It's that the oven produces an enormous flood of photons, and the frequency is tuned so that water molecules absorb them efficiently. The molecules absorb photon after photon, each one nudging the molecule's rotational energy slightly higher. Trillions upon trillions of these tiny nudges add up to the heat you feel when your soup gets warm. Above microwaves comes infrared radiation. This is the range from about 300 billion to about 430 trillion Hz. You cannot see infrared, but you can feel it as heat. Every warm object emits infrared radiation. You are radiating infrared right now. The warmth you feel when you hold your hand near a hot surface without touching it is infrared photons being absorbed by your skin. Each infrared photon carries more energy than a microwave photon, but still far less than a visible light photon. Then comes visible light. This occupies an extraordinarily narrow band of the electromagnetic spectrum, from about 430 trillion Hz for red light to about 750 trillion Hz for violet light. This is the only part of the entire electromagnetic spectrum that human eyes can detect. Everything else is invisible to us without instruments. Our eyes evolved to be sensitive to this range because it is the range of frequencies most strongly emitted by the Sun. The Sun's surface temperature of about 5,500 degrees Celsius means its radiation peaks in the visible range. Evolution tuned our eyes to the light that was most available. Within the visible range, different frequencies correspond to different colors. Red has the lowest frequency and the least energy per photon. Orange, yellow, green, blue, and violet follow in order of increasing frequency and increasing energy per photon. A violet photon carries nearly twice the energy of a red photon. That's why ultraviolet light, which sits just above violet in frequency, can damage your skin, while red light cannot. The individual photons pack enough energy to break chemical bonds in your DNA. Red light photons simply don't have enough energy per photon to do that damage, no matter how many of them you shine on your skin. Above visible light comes ultraviolet radiation, with frequencies from about 750 trillion to roughly 30 quadrillion hertz. Ultraviolet photons carry enough energy to ionize some atoms, meaning they can knock electrons free from atoms entirely. This is why prolonged sun exposure causes sunburn. The ultraviolet photons from the sun have enough energy to damage biological molecules. Your body responds with inflammation, which is the redness and pain of sunburn. Then come X-rays, with frequencies from about 30 quadrillion to about 30 quintillion hertz. Wilhelm Röntgen discovered X-rays in 1895, and they immediately revolutionized medicine. X-ray photons carry enough energy to penetrate soft tissue, but are absorbed by dense materials like bone. This is why X-ray images show your skeleton. Each X-ray photon carries thousands of times more energy than a visible light photon. This is why X-ray exposure must be carefully limited. Each individual photon has enough energy to ionize atoms and damage cells. At the top of the spectrum are gamma rays, with frequencies above about 30 quintillion hertz. These are produced in nuclear reactions, radioactive decay, and extreme astrophysical events. A single gamma-ray photon can carry millions or even billions of times more energy than a visible light photon. Gamma rays can penetrate deep into matter, ionizing atoms and breaking molecular bonds along the way. They are extraordinarily dangerous to living things and extraordinarily useful in physics, medicine, and astronomy. Every one of these, from radio to gamma, is the same fundamental thing: an excitation of the electromagnetic field, a photon. The difference between a harmless radio photon and a lethal gamma-ray photon is not that they are different kinds of particles. They are the same kind of particle. The difference is frequency. Only frequency. The gamma-ray photon is the electromagnetic field oscillating inconceivably fast, and so it carries enormous energy. The radio photon is the electromagnetic field oscillating slowly, and it carries almost none. This universality is one of the most beautiful features of electromagnetic theory. There is one field, there is one kind of excitation, and the entire vast range of electromagnetic phenomena, from the gentle warmth of a campfire to the destructive power of a nuclear blast's gamma radiation, is explained by a single variable: how fast the field oscillates. Now, let's address something that's easy to misunderstand. When we say frequency determines the photon's energy, it might sound like frequency is a separate property, something attached to the photon the way a price tag is attached to an item in a store, as if the photon exists independently and then has a frequency assigned to it. But that's not how it works. The frequency is not a label on the photon. The frequency is the photon. Remember what a photon is? It is a quantized excitation of the electromagnetic field. That excitation has a specific pattern of oscillation. The rate of that oscillation is the frequency. If you change the frequency, you don't have the same photon with a different label. You have a completely different photon, a different excitation, a different quantum state. The frequency defines the excitation. The excitation defines the photon. There is nothing left over once you specify the frequency, the direction of travel, and the polarization. There is no residual photon substance that exists independently of its frequency. This is crucial for understanding why photon energy is what it is. The energy is not something added to the photon from outside or stored inside it like fuel in a tank. The energy is inseparable from the oscillation. A faster oscillation is a higher energy oscillation. Not because the faster oscillation contains more stuff, but because that's what energy means in this context. Energy, for the electromagnetic field, is a measure of how vigorously the field is oscillating. A quantum of a vigorous oscillation carries more energy than a quantum of a gentle oscillation. This is not a mysterious transfer, it's definitional. The energy is the oscillation. The oscillation is the photon. The photon is the energy. They are three descriptions of the same physical reality. Let's also think about what Planck's constant tells us physically. Why does this particular number appear in the equation? What role does it play? Planck's constant sets the scale of quantum effects. It tells you how big the packets are. In a universe where Planck's constant was much larger, photons would carry much more energy at any given frequency, and quantum effects would be visible in everyday life. In a universe where Planck's constant was much smaller, photons would carry less energy, and quantum effects would be even harder to detect than they already are. In a universe where Planck's constant was zero, energy would not be quantized at all. The electromagnetic field could have any energy at any frequency. There would be no photons, no quanta, no quantum mechanics. The classical world would be all there is. But Planck's constant is not zero. It is small, incredibly small, but it is not zero. And because it is not zero, the electromagnetic field is quantized. Energy comes in packets. Light comes in photons. The universe is fundamentally quantum. The smallness of Planck's constant is why we don't notice quantum effects in daily life. When you turn on a light bulb, a staggering number of photons are emitted every second. A typical 100-watt incandescent bulb emits roughly 1 billion visible light photons per second. Each one carries a tiny quantum of energy, but there are so many of them that the light appears perfectly smooth and continuous. You don't see individual photons flickering on and off. You see a steady glow. This is like looking at a sand castle. Up close, you can see individual grains of sand, but from a normal distance, the surface looks smooth. The grains are so small and so numerous that the granularity disappears. Photons are the grains of light, and they are so tiny and so numerous in everyday situations that the quantum nature of light is completely hidden. But it's there, and when you design experiments carefully, you can see it. Scientists can detect individual photons. They can count them one by one. They can measure the energy of each one and confirm that it matches Planck's constant times the frequency exactly. These experiments have been done thousands of times with exquisite precision. The quantization of the electromagnetic field is one of the most thoroughly verified facts in all of science. There's another important aspect of the frequency-energy relationship that deserves attention. The relationship is universal. It applies to every photon ever created, everywhere in the universe, at all times. A photon emitted by a hydrogen atom in a laboratory on Earth has the same energy-frequency relationship as a photon emitted by a hydrogen atom in a galaxy 10 billion light-years away. Planck's constant doesn't change from place to place or time to time. The equation E equals h times F holds everywhere. This universality is a reflection of the fact that the electromagnetic field is the same everywhere. The rules governing its excitations are the same everywhere. Physics doesn't change depending on where you are. This principle, the uniformity of physical law across the universe, is one of the deepest and most tested assumptions in science. This universality is also what makes astronomy possible. When astronomers observe light from a distant star, they can measure its frequency. From that frequency, they know the energy per photon. They know which atomic transitions could have produced it. They can determine what elements are present in the star's atmosphere, how hot the star is, whether it's moving toward us, or away from us. All of this information is encoded in the frequencies of the photons the star emits. And it works because the frequency-energy relationship is the same there as it is here. If Planck's constant varied across the universe, astronomy as we know it would be impossible. So where are we now? We know that a photon is a quantized excitation of the electromagnetic field. We know that the energy of each photon is determined entirely by its frequency. We know the relationship is simple, direct, and universal. E equals h times f. And we know that frequency is not a label attached to a photon, but the defining characteristic of what the photon is. But this leads directly to the next question. If a photon's energy is set by its frequency, and the frequency is set at the moment the photon is created, then what determines the frequency? What physical process decides whether a particular excitation of the electromagnetic field will oscillate at 430 trillion Hz, producing a red photon, or at 300 quintillion Hz, producing a gamma ray? The answer is that the frequency is determined by the process that creates the photon, the birth event. The physical mechanism that excites the electromagnetic field in the first place. An electron dropping between energy levels in an atom produces a photon whose frequency exactly matches the energy difference between those levels. A particle accelerating in a magnetic field produces radiation at a frequency determined by how fast it's accelerating. A nuclear reaction releases energy at frequencies set by the binding energies involved. The photon doesn't choose its frequency. It doesn't generate its energy from some internal resource. It inherits both from whatever physical process brought it into existence. The photon is born with its energy already determined, and that energy is locked in for the rest of the photon's existence. This is the heart of the answer to our title question, and this is where we need to go next. Not just what determines the energy, but the specific physical mechanisms, the actual processes inside atoms, stars, and accelerating charges that create photons and set their energies. Because the photon doesn't get its energy from frequency in some abstract mathematical sense, it gets its energy from the concrete physical event that excites the electromagnetic field. And those events are where the real story lies. A photon is a quantized excitation of the electromagnetic field, and its energy is determined entirely by its frequency. But that raises a question that goes straight to the heart of our story. If the photon's energy is set by its frequency, and the frequency is set at the moment the photon is born, then where does the energy actually come from? Not in an abstract mathematical sense, in a physical, concrete, this is what happens in nature sense. What process gives the photon its energy? What event determines the frequency? What is the birth of a photon actually like? The answer is that a photon gets its energy from the physical process that creates it. Every photon in the universe was born from some event, some interaction, some transition, some acceleration, some reaction. And the energy the photon carries is precisely the energy that was released or transformed during that event. The photon doesn't manufacture energy. It doesn't pull energy from some reserve hidden in the fabric of space. It inherits its energy from its origin. The creation process sets the frequency, and the frequency determines the energy. The photon carries that energy away from its birthplace at the speed of light, delivering it to whatever eventually absorbs it, whether that's an atom in a distant telescope, a molecule in your retina, or a grain of dust floating between the stars. Let's go through the major physical processes that create photons, because each one illustrates this principle in a different and illuminating way. The most important photon creation process for understanding quantum physics is the atomic transition. This is where an electron inside an atom drops from a higher energy level to a lower energy level, and the energy difference is carried away by a newly created photon. To understand this, you need to know a little about how atoms work. In the early 1900s, after Ernest Rutherford discovered that atoms have a tiny, dense nucleus surrounded by electrons, there was a crisis in physics. Classical electromagnetic theory said that an electron orbiting a nucleus should radiate energy continuously. A charged particle moving in a circle is accelerating, and accelerating charges emit electromagnetic radiation. That's what Maxwell's equations demand. The electron should spiral inward, emitting radiation all the way, and crash into the nucleus in a tiny fraction of a second. Atoms should be unstable. They should collapse almost instantly. But they don't. Atoms are stable. They hold together. They form molecules, rocks, planets, stars, and people. Something was deeply wrong with the classical picture. In 1913, Niels Bohr proposed a radical solution. He suggested that electrons in atoms don't occupy just any orbit. They occupy specific allowed orbits, each with a definite energy. An electron in one of these orbits doesn't radiate, it just stays there, stable, indefinitely. This directly contradicted Maxwell's equations, and Bohr knew it. He couldn't explain why electrons in atoms didn't radiate. He simply postulated that they didn't, and showed that this postulate, combined with quantum ideas from Planck and Einstein, explained the observed properties of hydrogen spectacularly well. Bohr's model was eventually replaced by the full quantum mechanical description, developed in the 1920s, which explained why electrons occupy specific energy levels. The answer lies in the wave nature of matter. Electrons are not tiny balls orbiting the nucleus like planets orbiting a star. They are quantum objects described by wave functions, mathematical objects that encode the probability of finding the electron in various places around the nucleus. Only certain wave function patterns are allowed, those that satisfy the boundary conditions of the atom. Each allowed pattern corresponds to a specific energy level. The electron can occupy any of these levels, but it cannot exist between them. The energy levels are discrete, like the rungs of a ladder. You can stand on one rung or another, but not between rungs. When an electron is in a higher energy level and drops to a lower one, the atom loses a specific amount of energy. That energy has to go somewhere. It goes into the electromagnetic field. The field gets excited. A photon is born, and the photon's energy is exactly equal to the energy difference between the two levels. Not approximately, exactly. If the higher level has an energy of 10 units, and the lower level has an energy of 7 units, the photon carries away exactly 3 units of energy. This determines the photon's frequency. E equals h times f, so f equals E divided by h. The frequency is fixed. The photon has no choice in the matter. It must have the frequency corresponding to the energy difference, no more, no less. This is why atoms emit light at very specific frequencies. If you heat hydrogen gas until it glows and spread that light through a prism, you don't see a smooth rainbow. You see a series of bright lines at specific, discrete frequencies. Each line corresponds to a specific electron transition. An electron dropping from level 3 to level 2 in hydrogen produces a photon with a wavelength of 656 nanometers. That's a specific shade of red called hydrogen alpha. An electron dropping from level 4 to level 2 produces a photon at 486 nanometers, a blue-green color. Each transition produces a photon at one precise frequency, because the energy levels in hydrogen have specific, fixed energy values. Johann Balmer figured out the mathematical pattern of hydrogen's visible spectral lines in 1885, decades before anyone understood why the pattern existed. When Bohr's model explained the pattern in 1913, it was one of the great triumphs of early quantum theory. Today, quantum mechanics can predict these energy levels and transition frequencies with extraordinary precision, matching experimental measurements to many decimal places. The point for our story is this. When a hydrogen atom emits a red hydrogen alpha photon, the energy of that photon comes directly from the atom. The electron was in a higher energy state. The atom had more energy. Then the electron dropped to a lower state. The atom had less energy. The difference went into the photon. The photon's energy is the atom's lost energy. Nothing was created from nothing. Energy was transformed. It moved from the electron's orbital energy into the electromagnetic field's oscillation. The photon was born carrying away exactly the energy the atom gave up. This process is happening right now, all around you, all across the universe. Every time you see color, you are seeing photons that were born in atomic transitions. The red glow of a neon sign comes from electrons in neon atoms dropping between specific energy levels, emitting photons at specific frequencies. The yellow of a sodium streetlight comes from a particular transition in sodium atoms. The blue of a gas flame comes from molecular transitions in the combustion products. The light from every star in the sky comes from atoms in the star's outer layers undergoing transitions, emitting photons at the frequencies corresponding to the energy differences in those atoms. Astronomers can identify the chemical composition of a star billions of light years away by analyzing which frequencies appear in its light, because each element has a unique set of energy levels and therefore a unique set of emission frequencies. The photon carries a fingerprint of the atom that created it. But atomic transitions are not the only way photons are born. There is a completely different mechanism that produces electromagnetic radiation, one that doesn't require atoms at all. It requires only a charged particle that is accelerating. Maxwell's equations tell us that whenever a charged particle accelerates, it emits electromagnetic radiation. Acceleration here means any change in velocity, speeding up, slowing down, or changing direction. The radiation carries energy away from the charged particle. This is not a quantum effect. It was understood classically, long before quantum mechanics, but it remains true in the quantum picture. When a charged particle accelerates, the electromagnetic field around it gets disturbed. That disturbance propagates outward as radiation. In the quantum description, this radiation consists of photons. The frequency and energy of the emitted photons depend on the details of the acceleration. How rapidly is the particle accelerating? How much energy is available to be radiated? The faster and more violent the acceleration, the higher the frequency of the emitted radiation, and therefore the higher the energy of each photon. Consider an electron moving through a magnetic field. The field exerts a force perpendicular to the electron's motion, curving its path into a spiral. This constant change of direction is acceleration, and the accelerating electron emits radiation called synchrotron radiation, named after the particle accelerators where it was first observed. The frequency depends on the electron's speed and the strength of the magnetic field. Faster electrons in stronger fields produce higher frequency radiation. Synchrotron radiation is ubiquitous in astrophysics. Electrons spiraling in the magnetic fields around black holes, neutron stars, and in the jets of active galaxies produce synchrotron radiation ranging from radio waves to X-rays. Each photon gets its energy from the kinetic energy of the electron. As the electron radiates, it loses energy and slows down. The energy didn't appear from nowhere. It was transferred from the electron's motion into the electromagnetic field. The photon carries away energy that the electron once had. There's another form of radiation from accelerating charges that's particularly important in astrophysics and medicine. When a fast-moving electron passes close to an atomic nucleus, the electric field of the nucleus deflects the electron. The electron swerves, decelerating sharply. This sudden deceleration produces a photon. This process is called Bremsstrahlung, a German word meaning breaking radiation. The energy of the Bremsstrahlung photon depends on how much the electron slows down during the encounter. If the electron loses a lot of kinetic energy, the photon has high energy and high frequency. If the electron only grazes the nucleus and loses a little energy, the photon has low energy and low frequency. Because electrons can lose varying amounts of energy in these encounters, Bremsstrahlung produces a continuous spectrum of photon energies, unlike atomic transitions, which produce photons only at specific discrete energies. This is why X-ray machines work. In an X-ray tube, electrons are accelerated to high speeds and slammed into a metal target. When they decelerate violently upon hitting the target's atoms, they emit Bremsstrahlung radiation in the X-ray frequency range. The photons get their energy from the kinetic energy of the electrons, which were accelerated using electrical energy from a power supply. At every step, energy is being transformed, never created from nothing. Now let's consider thermal radiation, which is the most common source of photons in the universe. Every object with a temperature above absolute zero emits electromagnetic radiation. You emit it. The walls around you emit it. The Earth emits it. The Sun emits it. Stars emit it. Even the cold gas between galaxies emits it, though very weakly. Thermal radiation arises because the atoms and molecules in any warm object are in constant random motion. They vibrate, rotate, collide, and jostle. And since atoms contain charged particles, electrons and protons, this random thermal motion involves constant acceleration of charges. Every vibration is an acceleration. Every collision involves a rapid change of velocity. Each of these accelerations produces electromagnetic radiation. The cumulative effect of trillions upon trillions of randomly accelerating charges is a smooth, continuous spectrum of radiation whose peak frequency depends on temperature. This is described by Wien's law, which states that the peak frequency of thermal radiation is proportional to the temperature of the emitting object. A cool object, like a human body, at around 37 degrees Celsius, emits mostly infrared radiation with a peak wavelength around 10 micrometers. You can't see this radiation with your eyes, but infrared cameras can detect it. A hotter object, like an incandescent light bulb filament, at around 2,700 degrees Celsius, emits radiation that peaks in the infrared but extends into the visible range, producing the warm yellowish glow you see. A very hot object, like the surface of the Sun, emits the familiar white glow of sunlight, the combined effect of thermal photons spanning the full visible range and beyond. At even higher temperatures, the peak shifts to shorter wavelengths and higher frequencies. A star with a surface temperature of 30,000 degrees Celsius emits mostly ultraviolet radiation. The hottest objects in the universe, like the accretion disks around black holes at temperatures of millions of degrees, emit primarily X-rays. In every case, the photons get their energy from the thermal energy of the emitting object. The atoms are jiggling because they have thermal energy. That thermal energy comes from whatever heated the object. For the Sun, the thermal energy comes from nuclear fusion reactions in the core. For an incandescent bulb, it comes from electrical resistance heating the filament. For your body, it comes from metabolic chemical reactions. The photons carry away a portion of that thermal energy. This is why hot objects cool down if they're not continually heated. They're radiating their thermal energy away as photons. Each photon takes a little bit of thermal energy with it, and the object gets slightly cooler. The Sun is a spectacular example of this chain of energy transformation. Deep in the Sun's core, hydrogen nuclei fuse together to form helium. This nuclear fusion process converts a tiny amount of mass into energy, following Einstein's equation E equals mc squared. The mass of 4 hydrogen nuclei is slightly more than the mass of 1 helium nucleus. That mass difference, about 0.7% of the original mass, is converted into energy. This energy emerges primarily as high-energy gamma-ray photons and as the kinetic energy of the fusion products. But the gamma-ray photons born in the Sun's core don't simply fly straight out. The Sun's interior is incredibly dense. A photon emitted in the core almost immediately collides with an atom, is absorbed, and then re-emitted, usually at a slightly lower frequency. This happens again and again and again. The photon is absorbed, re-emitted, bouncing around randomly in a process that takes, on average, roughly 100,000 to 200,000 years to carry energy from the core to the surface. Along the way, each absorption and re-emission event transforms the photon. A single gamma-ray photon born in the core is eventually converted into millions of lower-energy photons by the time the energy reaches the surface. When the energy finally reaches the Sun's surface, it is emitted as the thermal radiation we see as sunlight. These visible light photons carry energy that originated in nuclear fusion reactions in the core. The photons themselves are different from the gamma-ray photons born in the core. They have much lower frequency and much less energy per photon. But the total energy is conserved. The energy that started as nuclear binding energy was converted into gamma-ray photon energy, which was progressively converted into many lower energy photons, which were finally emitted from the surface as sunlight. The photon you see when you look at the Sun carries energy that was released by nuclear fusion deep in the Sun's interior. Energy that took 100,000 years or more to work its way to the surface and 8 minutes and 20 seconds to cross the space between the Sun and Earth. This is a vivid illustration of our central principle. The photon gets its energy from the process that creates it. The sunlight photon was created by a thermal emission process at the Sun's surface. The thermal energy at the surface came from energy transported from the core. The energy in the core came from nuclear fusion. The nuclear binding energy came from the mass difference between hydrogen and helium. At every step, energy is being transformed, passed from one form to another. The photon is the carrier, the messenger, the delivery mechanism. It doesn't generate the energy, it inherits it. Now let's look at an even more dramatic process. Matter-antimatter annihilation. When a particle meets its antiparticle, they can annihilate each other, converting their entire rest mass into energy. An electron has a rest mass energy of about 0.511 mega-electron volts. A positron, the electron's antiparticle, has the same rest mass energy. When an electron and positron meet and annihilate, their combined rest mass energy of about 1.022 mega-electron volts is converted into photons. Typically, 2 gamma-ray photons are produced, each carrying about 0.511 mega-electron volts of energy, flying off in opposite directions. Where did the photons get their energy? From the mass of the electron and positron. Mass is a form of energy, and in this process, it is converted entirely into electromagnetic energy. The photons carry away the energy that was formerly locked up in the mass of the two particles.
Nothing was created or destroyed in the total energy accounting. Mass energy became photon energy. The particles vanished and the electromagnetic field got excited. 2 new photons were born, each carrying exactly half the total energy that was available. This is one of the cleanest examples of where photon energy comes from. The energy comes from mass. Einstein's famous equation, E equals mc squared, tells you exactly how much energy is available when mass is converted. The speed of light squared is an enormous number, which is why even a tiny amount of mass corresponds to a vast amount of energy. The annihilation of an electron and positron, 2 particles far too small to see, produces gamma-ray photons with enough energy to be detected by instruments halfway across a laboratory. There are other photon creation processes worth understanding.
Nuclear transitions, analogous to atomic transitions but involving the nucleus rather than the electron cloud, produce gamma-ray photons. When a nucleus drops from an excited state to a lower energy state, the energy difference is carried away by a gamma-ray photon. These energy differences are much larger than atomic energy differences because nuclear forces are much stronger than electromagnetic forces, so the resulting photons have much higher frequencies and energies. Radioactive decay processes also produce photons. In gamma decay, a nucleus in an excited state emits a gamma-ray photon to reach a more stable configuration. The photon's energy is the difference between the nuclear energy levels involved. In other types of radioactive decay, charged particles are emitted at high speeds, and these particles can subsequently produce photons through Bremsstrahlung or other processes. The energy always traces back to the nuclear binding energy, the energy stored in the configuration of protons and neutrons within the nucleus. Cherenkov radiation is another fascinating photon production mechanism. When a charged particle travels through a transparent medium, like water or glass, faster than light travels through that medium, it produces a cone of electromagnetic radiation, somewhat analogous to the sonic boom produced by an object moving faster than the speed of sound. The photons in Cherenkov radiation get their energy from the kinetic energy of the fast-moving particle. As the particle emits radiation, it slows down. Energy is transferred from the particle's motion to the electromagnetic field. Cherenkov radiation produces the eerie blue glow sometimes seen in the water surrounding nuclear reactors, where fast electrons produced by nuclear reactions travel faster than light does in water. Every single one of these processes, atomic transitions, accelerating charges, thermal radiation, nuclear reactions, matter-antimatter annihilation, Cherenkov radiation, follows the same fundamental principle. The photon gets its energy from the physical process that creates it. The energy doesn't come from inside the photon. It doesn't come from some hidden compartment. It comes from whatever event excited the electromagnetic field. The process determines the frequency. The frequency determines the energy, and the photon carries that energy away at the speed of light. This leads to an important distinction that's worth making explicit, because it clears up a misconception that even some popular science explanations perpetuate. There is a fundamental difference between saying a photon carries energy and saying a photon has internal fuel. A photon carries energy the way a wave carries a disturbance, not the way a truck carries freight. When a wave crosses a lake, the wave carries energy from one shore to the other. But the wave doesn't have a fuel tank. It doesn't burn anything. It doesn't consume itself. The energy is in the pattern of motion of the water. The wave is the pattern of motion. The energy and the wave are inseparable aspects of the same phenomenon. A photon is exactly like this. It carries energy from where it was created to where it is absorbed. The energy is not cargo, it is the oscillation itself. The photon doesn't burn fuel as it travels, it doesn't lose energy along the way in empty space. A photon, traveling through the vacuum of space for 1 billion years, carries exactly the same energy when it arrives as it did when it was emitted. It doesn't get tired. It doesn't run out. The oscillation doesn't decay. The frequency doesn't change. In a vacuum, a photon is a perfectly lossless carrier of energy. This is remarkable. It means that a photon emitted by a star 1 billion light-years away delivers to your telescope the exact energy it was born with. The energy that originated in a nuclear reaction or an electron transition in a distant star is faithfully transported across 1 billion light-years of empty space and deposited, unchanged, into your detector. The electromagnetic field is the most efficient energy transport system in the universe. No loss, no degradation, no friction, no fuel consumed. The energy rides the oscillation of the field, and the field carries it perfectly. There is one important caveat. If the space itself is expanding, as it is in our universe, then the photon's wavelength gets stretched along with the expanding space. A longer wavelength means a lower frequency, and a lower frequency means less energy per photon. This is the cosmological redshift. Photons from very distant galaxies arrive with longer wavelengths and less energy than they had when they were emitted. But this energy hasn't been lost in the usual sense. It hasn't been absorbed or dissipated. The expansion of space has reduced the photon's frequency, and with it, its energy. Where that energy goes is actually a subtle question in general relativity. The energy isn't transferred to something else. It's a consequence of the changing geometry of space-time. The photon still carries the energy corresponding to its current frequency. It just has a different frequency now than it did when it was born. Setting aside cosmological effects, the core principle stands. A photon is born in a physical process. That process determines the frequency. The frequency determines the energy. The photon carries that energy faithfully until it is absorbed. And when it is absorbed, the energy goes into whatever absorbed it, raising an electron's energy, heating a surface, triggering a chemical reaction. Energy is never created. Energy is never destroyed. It flows from source to photon to absorber, transformed at each step, but always conserved. This picture explains something that might have puzzled you at the beginning. Why do different photons carry such wildly different amounts of energy? Why does a gamma-ray photon carry 1 billion times more energy than a visible light photon? Not because gamma-ray photons are made of different stuff, not because they have bigger fuel tanks or stronger engines, but because the processes that create them release more energy. A nuclear transition releases far more energy than an atomic transition, so the resulting photon has a much higher frequency and much more energy. An electron-positron annihilation releases the entire rest mass energy of 2 particles, so the resulting photons are tremendously energetic. A radio transmitter gently oscillates electrons back and forth in an antenna, producing very low frequency, very low energy photons. The energy of the photon reflects the energy of its origin. Nothing more, nothing less. The photon is a messenger. It tells you about the event that created it. Its frequency is a record of the energy that was released. Its very existence is proof that somewhere, somewhen, a physical process disturbed the electromagnetic field with exactly that amount of energy. When you look at a photon, you are looking at the signature of its birth. And yet, for all this explanatory power, for all the elegance of the picture, there remains a deep puzzle. A photon has no mass. It has energy. It has momentum. It travels at the speed of light. How is any of this possible? In everyday experience, energy and momentum are properties of massive things, things with weight, things with substance. A photon has no rest mass at all. It is, in a sense, made of nothing. And yet it carries energy so real that it can warm your skin, trigger chemical reactions in your eyes, power solar panels, and destroy molecules. How does something with no mass carry real, physical, measurable energy and momentum? That question takes us to Einstein, to the deep relationship between energy, mass, and momentum, and to one of the most beautiful ideas in all of physics. Here is the puzzle that sits at the center of everything we've discussed. A photon has no rest mass, not a tiny amount, not an amount too small to measure, exactly 0. A photon is, by any classical definition, made of nothing substantial. It has no weight. It has no stuff. You cannot put it on a scale. You cannot hold it in your hand. And yet a photon carries energy. Real energy. Energy that can warm your skin, knock electrons out of metal, power a spacecraft, trigger the chemical reactions that let you see. A photon also carries momentum, real momentum, enough momentum that light can push objects, can exert pressure, can move physical things from one place to another. How is this possible? How can something with no mass carry energy and momentum? The answer lies in one of the most profound and misunderstood equations in physics. Not the famous one you've probably seen on t-shirts and coffee mugs, not E equals mc squared, though that equation is part of the story. The full equation, the complete energy-momentum relation that Einstein derived from special relativity. And understanding this equation changes everything about how you think about the relationship between mass and energy. Most people know E equals mc squared. It's the most famous equation in the world. It says energy equals mass times the speed of light squared. And most people interpret it to mean that mass and energy are the same thing, that mass is just frozen energy, and energy is just liberated mass. This interpretation isn't exactly wrong, but it's dangerously incomplete. Because if energy equals mass times the speed of light squared, and a photon has zero mass, then a photon should have zero energy. And that's obviously not true. Photons carry energy. We've spent considerable time establishing that fact. So something must be missing from the famous equation. What's missing is that E equals mc squared is not the full equation. It's a special case. It applies only to objects that are sitting still, not moving, at rest. The m in E equals mc squared is the rest mass, the mass an object has when it's not moving relative to you. For an object at rest, its energy equals its rest mass times the speed of light squared. This is the rest energy. It's the energy locked up in the object's mass itself, separate from any kinetic energy from motion. And for a photon, this rest energy is zero, because the rest mass is zero. But a photon is never at rest. From the instant it comes into existence to the instant it is absorbed, a photon travels at exactly the speed of light, always, without exception. You cannot slow a photon down. You cannot bring it to a stop. The concept of a stationary photon doesn't make physical sense within relativity. A photon at rest would not be a photon. It would be nothing. So applying the rest energy equation to a photon gives you a meaningless answer, because the premise of the equation, that the object is at rest, doesn't apply. The full energy-momentum relation from special relativity is more complete. It says that the total energy squared equals the momentum times the speed of light, all squared, plus the rest mass times the speed of light squared, all squared. Written symbolically, total energy squared equals p(c) squared plus m(c) squared squared, where p is momentum, c is the speed of light, and m is the rest mass. This is the real equation. E equals mc squared is just what you get when you set the momentum to zero, which means the object is at rest. Now watch what happens when you apply the full equation to a photon. The rest mass of a photon is zero, so the second term, the mass term, vanishes entirely. You're left with total energy squared equals p(c) squared. Take the square root of both sides and you get total energy equals momentum times the speed of light. E equals p times c. This is the energy equation for a photon. It tells you that all of a photon's energy is carried as momentum. There is no rest energy contribution because there is no rest mass. The photon's energy is entirely in its motion, in its momentum. A photon is pure kinetic energy, pure momentum, traveling at the speed of light with no mass whatsoever. This is a completely different relationship from what we're used to. For a baseball or a planet, kinetic energy depends on mass and velocity. For a photon, there is no mass. The energy depends on momentum, and the momentum depends on frequency. E equals h times f, and E equals p times c. So momentum equals h times f divided by c. Higher frequency, more momentum. Lower frequency, less momentum. The frequency sets everything. Let's sit with this for a moment, because it's genuinely remarkable. In everyday physics, momentum is mass times velocity. A heavy object moving fast has a lot of momentum. A light object moving slowly has very little. Momentum is the property that makes a bowling ball hard to stop and a ping pong ball easy to stop. It measures how much push something has, and we normally think of it as requiring mass. You need stuff to have momentum. You need substance. But a photon has momentum without mass. Its momentum comes from its energy, and its energy comes from its frequency. This isn't an approximation or a theoretical speculation. It's a measured, confirmed, experimentally verified fact. We know photons carry momentum because we can see them pushing things. In 1901, the physicists Ernest Nichols and Gordon Hull measured the pressure of light on a small mirror in a carefully designed experiment, confirming that light does indeed exert a force. Around the same time, the Russian physicist Pyotr Lebedev independently measured radiation pressure. The pressure was exactly what Maxwell's electromagnetic theory predicted, and exactly what the photon momentum equation gives. Light pushes things. Each photon delivers a tiny impulse when it's absorbed or reflected. One photon's push is negligible, but enough photons, concentrated on a surface, create measurable pressure. In 1923, Arthur Compton provided some of the most dramatic evidence for photon momentum. He directed X-ray photons at electrons and observed what happened. If a photon were just a wave, it would scatter off the electron in a predictable way. But Compton found something different. The scattered X-rays had a longer wavelength, meaning a lower frequency, meaning less energy per photon. Meanwhile, the electrons recoiled as if they'd been hit by a particle. The photon bounced off the electron like a billiard ball, losing some energy and momentum to the electron in the process. The angles and energies matched perfectly with conservation of energy and conservation of momentum, treating the photon as a particle with momentum equal to its energy divided by the speed of light. Compton's scattering was decisive. It showed beyond any reasonable doubt that photons carry momentum, that they interact with matter the way particles with momentum interact, and that the momentum is exactly what special relativity predicts for a massless particle. Compton received the Nobel Prize for this work in 1927. Radiation pressure isn't just a laboratory curiosity.
It has real consequences throughout the universe. Inside stars, radiation pressure from photons produced by nuclear fusion pushes outward against the star's own gravity. In massive stars, this outward photon pressure is enormous. It's one of the main forces preventing the star from collapsing under its own weight. The star exists in a balance between gravity pulling inward and radiation pressure pushing outward. If nuclear reactions stop, radiation pressure drops, gravity wins, and the star collapses. This is what happens in a supernova. Solar radiation pressure pushes on comets' dust tails, pointing them away from the sun. It exerts a measurable force on spacecraft, a force that mission planners must account for when calculating trajectories. There are even proposals to use radiation pressure for propulsion. Solar sails, large, thin, reflective sheets deployed in space, would catch sunlight the way a boat's sail catches wind. Each photon that bounces off the sail transfers a tiny amount of momentum. Enough photons, over enough time, could accelerate a spacecraft to significant speeds without any fuel. The Japanese spacecraft Icaros, launched in 2010, successfully demonstrated solar sail propulsion by unfurling a thin membrane in space and using sunlight pressure for acceleration. The photons pushing on that sail had no mass, yet they delivered enough momentum to change the spacecraft's velocity. Massless particles pushing a physical object through space. This would seem like magic if we didn't understand the physics behind it, but it's not magic. It's a direct consequence of the energy-momentum relation for massless particles. There are even more striking demonstrations of photon momentum at smaller scales.
In 1986, the physicist Arthur Ashkin developed a technique called optical trapping, sometimes known as optical tweezers. The idea is remarkably simple in principle. You take a tightly focused laser beam and aim it at a microscopic object, a bacterium, a tiny glass bead, a single biological cell. The photons in the laser beam carry momentum. When they pass through the object, they are refracted, changing direction. That change of direction means a change of momentum, and by Newton's third law, the object experiences a force in the opposite direction. With careful focusing, this force can trap the object in 3 dimensions, holding it in place using nothing but light. Think about what this means. Photons, massless particles with 0 rest mass, are physically gripping a microscopic object and holding it still against thermal fluctuations. You can move the laser beam and the object moves with it. You can use optical tweezers to pick up individual cells, to stretch single molecules of DNA, to measure the forces generated by molecular motors inside living cells. Ashkin shared the Nobel Prize in Physics in 2018 for this invention. It was a Nobel Prize awarded, in essence, for using the momentum of massless particles to manipulate matter. Laser cooling is another extraordinary application. When atoms move toward a laser beam tuned to just below an atomic resonance frequency, the atoms preferentially absorb photons head-on. Each absorbed photon delivers a tiny kick of momentum opposing the atom's motion. The atom slows down slightly. Repeat this process millions of times per second with carefully arranged laser beams from all directions, and you can slow atoms from speeds of hundreds of meters per second to nearly a standstill. Temperatures drop to millionths of a degree above absolute zero. Atoms are brought almost to rest using nothing but the momentum of massless photons. This technique has enabled some of the most precise measurements in all of physics, from atomic clocks accurate to 1 second in billions of years, to the observation of exotic quantum states of matter like Bose-Einstein condensates. Now, let's address a deeper conceptual issue that trips up many people. If photons have no mass, why can't we just say they have no substance and leave it at that? Why do physicists insist that photons are real physical things if they have no mass? The answer is that mass is not the defining feature of physical reality. Energy and momentum are. Something is physically real if it carries energy and momentum, if it can interact with other things, if it can change the state of matter. Photons do all of these things. They carry energy. They carry momentum. They knock electrons out of atoms. They heat surfaces. They trigger chemical reactions. They push spacecraft. They are as real as anything else in the universe. They simply happen to have no rest mass. This overturns a deeply intuitive assumption that most people carry. The assumption that real things must have mass, that substance requires weight, that you need stuff to be something. Photons show that this assumption is wrong. You can have something with no mass at all that nevertheless interacts with the physical world in concrete, measurable ways. The electromagnetic field doesn't need mass to carry energy and momentum. It does it through oscillation, through vibration, through the rhythmic dance of electric and magnetic fields propagating through space at the speed of light. This connects back to a crucial point. The photon is not a container carrying energy. It is the energy. Or more precisely, it is a quantum of energy in the electromagnetic field. The energy is in the oscillation, and the oscillation is the photon. Mass is simply not part of this picture. The field oscillates. The oscillation propagates. Energy and momentum move from one place to another. No mass required. It's worth understanding why massless particles must travel at the speed of light, because this is not arbitrary. It follows directly from the structure of spacetime as described by special relativity. In special relativity, the speed of light is not just a fast speed. It is a structural feature of spacetime. It is the speed at which causality propagates. It is the conversion factor between space and time. Spacetime is a single, unified entity, and the speed of light is the constant that relates spatial distances to temporal intervals. When Einstein discovered that the speed of light is the same for all observers, regardless of their motion, he wasn't just finding a fast speed. He was uncovering a fundamental property of the universe itself. Massive particles can travel at any speed below the speed of light. As they go faster, they need more and more energy to accelerate further. The energy required grows without limit as you approach light speed. You'd need infinite energy to reach it. So massive particles can never get there. But massless particles face the opposite constraint. They cannot travel slower than the speed of light. For a massless particle, there is no valid frame of reference in which it is at rest. The mathematics of special relativity simply doesn't allow it. If you try to calculate what happens to a massless particle at any speed other than the speed of light, the equations become inconsistent. The only self-consistent solution is for massless particles to travel at exactly the speed of light. Always. No exceptions. This is why photons travel at the speed of light. Not because they choose to, not because something accelerates them to that speed, but because the structure of space-time demands it. A massless excitation of any field must propagate at the speed of light. It's built into the geometry of the universe. A photon is born traveling at the speed of light. It lives its entire existence traveling at the speed of light. And it is absorbed while traveling at the speed of light. It never experiences anything else. There is a fascinating consequence of this that's worth noting. From the photon's own perspective, if such a perspective could be defined, no time passes. At the speed of light, time dilation becomes infinite.
A photon emitted by a star a billion light-years away experiences zero elapsed time between its emission and its absorption. To the photon, its birth and its death are the same event. It crosses the entire universe in no time at all from its own frame. But of course, saying things from the photon's perspective is physically problematic. Special relativity says you cannot construct a valid reference frame moving at the speed of light. The photon doesn't have a perspective in the way that a person on a train has a perspective. This is one of those places where our language and intuition fail. The photon exists. It travels. It carries energy. But it doesn't experience its journey the way a massive observer would. Let's now bring everything together into a unified picture of what a photon is and where its energy comes from. A photon is a quantized excitation of the electromagnetic field. The electromagnetic field is a real physical entity that fills all of space. When something disturbs this field, when a charged particle accelerates, when an electron transitions between energy levels in an atom, when a nuclear reaction releases binding energy, when matter and antimatter annihilate, the field gets excited. A ripple forms. That ripple is a photon. The photon's energy is determined by the frequency of the excitation, the rate at which the electromagnetic field oscillates in that particular quantum of vibration. The relationship is simple and exact. Energy equals Planck's constant times frequency. This frequency is not a property added to the photon after its creation. It is the defining characteristic of what the photon is. Change the frequency and you have a different photon entirely. The frequency itself is set by the physical process that creates the photon. An electron dropping between energy levels in a hydrogen atom releases a photon whose frequency corresponds precisely to the energy difference between those levels. A fast electron decelerating near a nucleus releases a Bremsstrahlung photon, whose frequency depends on how much kinetic energy the electron lost. A nuclear transition releases a gamma-ray photon, whose frequency reflects the energy gap between nuclear states. An electron-positron annihilation creates photons whose combined energy equals the total rest mass energy of both particles. In every case, the photon inherits its energy from its birth event. The creation process is the energy source. The photon is the energy carrier. The photon has no rest mass.
This does not mean it has no energy or momentum. The full energy-momentum relation from special relativity shows that for massless particles, energy equals momentum times the speed of light. All of a photon's energy is carried as momentum. This momentum is real and measurable. Photons push things. They exert pressure. They transfer momentum to surfaces when absorbed or reflected. The momentum of sunlight holds up the outer layers of stars against gravitational collapse and can propel spacecraft through the void of space. Because the photon has no rest mass, it must travel at the speed of light. This is not a choice or an accident. It is a requirement imposed by the structure of space-time itself. Massless particles cannot travel at any other speed. They are born at light speed, they live at light speed, and they are absorbed at light speed. The photon carries energy without internal fuel, without hidden reserves, without any stored substance. The energy is not inside the photon. The energy is the photon. It is the oscillation of the electromagnetic field at a specific frequency, propagating through space at the speed of light. Remove the energy and there is no photon. The field returns to its ground state. The excitation vanishes. There is nothing left over. This picture resolves the apparent paradox we started with. How can something with no mass, no internal parts, and no hidden structure carry energy? The answer is that energy does not require mass. Energy does not require substance. Energy does not need to be stored inside a container. Energy can exist as a pattern, as an oscillation, as a quantized vibration in a field. The electromagnetic field provides the medium. Quantum mechanics provides the rules of quantization. Special relativity provides the relationship between energy, momentum, and mass. And together they produce the photon, a massless, structureless quantum of electromagnetic energy that carries a precisely determined amount of energy and momentum from its point of creation to its point of absorption. Every photon in the universe tells you a story about its origin. The frequency of a photon from a hydrogen lamp tells you about the energy levels in hydrogen atoms. The frequency of an X-ray photon from a hospital machine tells you about high-speed electrons slamming into metal targets. The frequency of a gamma-ray photon from a radioactive nucleus tells you about the energy differences between nuclear states. The frequency of a photon from the cosmic microwave background tells you about the temperature of the universe 380,000 years after the Big Bang. The photon is a faithful messenger, carrying the signature of its birth across any distance, for any length of time, at the speed of light, without losing a single quantum of the energy it was born with. When you step outside on a sunny day and feel warmth on your face, you are absorbing photons. Each one was born in the outer layers of the sun, created by thermal processes powered ultimately by nuclear fusion in the sun's core. Each one traveled 150 million kilometers through the vacuum of space, taking 8 minutes and 20 seconds to make the journey. Each one carried energy determined by its frequency, energy that originated in the conversion of hydrogen to helium deep inside a star. And when that photon is absorbed by your skin, its energy becomes your thermal energy. The oscillation of the electromagnetic field ends. The photon ceases to exist, but the energy continues, now warming your skin, now part of you. This is the answer to our title question. Where does a photon get its energy from? From the physical process that creates it. An electron transition, an accelerating charge, a nuclear reaction, a matter-antimatter annihilation, any event that excites the electromagnetic field. The process determines the frequency determines the energy. The photon carries that energy as a quantized oscillation of the field, traveling at the speed of light, massless yet substantial, empty yet full, a vibration in the fabric of the universe, carrying energy from one corner of reality to another. The photon is one of the simplest things that exists. It has no internal parts, no structure, no subcomponents. It is defined by a handful of properties: frequency, direction, polarization. And yet, from this simplicity emerges the richness of everything we see. Every color in every sunset, every image on every screen, every signal in every fiber optic cable, every warmth felt from every fire, every piece of information carried by every beam of starlight across billions of light years. All of it is photons. All of it is quantized excitations of the electromagnetic field. All of it is energy, born from physical processes, carried at the speed of light, and delivered to whatever absorbs it. The universe is filled with photons. There are roughly 400 photons from the cosmic microwave background in every cubic centimeter of space. For every atom in the observable universe, there are roughly 1 billion cosmic microwave background photons. Photons are the most numerous particles in the universe, and every single one of them got its energy from the process that created it, carrying a precise quantum of electromagnetic energy determined by its frequency, traveling at the speed of light, through a universe made of fields. You are bathed in photons right now. Infrared photons from the walls around you, visible photons from your screen or your lamp, radio photons from Wi-Fi signals and cellular towers, cosmic microwave background photons that have been traveling for 13.8 billion years, remnants of the early universe that have crossed the entire history of cosmic time to be here, in this room, passing through your body at this very moment. Each one carrying the energy of its birth, each one a quantum of oscillation in a field that fills all of space. Each one a messenger from the event that created it. There is something quietly astonishing about all of this. We began with a simple question: where does a photon get its energy from? And the answer, once you follow it all the way down, connects nearly everything in physics. It connects quantum mechanics to electromagnetism, to special relativity, to the structure of atoms, to the physics of stars. A single question about a single massless particle pulls on threads that run through the entire fabric of our understanding of nature. And yet the answer itself is not complicated. It is not buried in mathematics so dense that only specialists can appreciate it. The photon gets its energy from the process that creates it. The process sets the frequency. The frequency sets the energy. The photon carries that energy through the universe at the speed of light, faithfully and without loss, until it is absorbed. Energy is transformed at each step, but never created and never destroyed. The simplicity of this answer is itself remarkable. The deepest truths in physics often are simple. Not easy to discover, not obvious, not intuitive, but simple once you see them. That the energy of light comes from the events that produce it, and that this energy is encoded in the frequency of an oscillation in a field that fills all of space, is one of those truths. It is elegant. It is complete. And it is, as far as anyone has ever been able to measure, exactly correct. A photon is not a tiny ball of light carrying fuel. It is a vibration in reality itself. And its energy is the echo of whatever set reality vibrating.